Let us start with the vector v. A vector may be regarded as an object with a magnitude and a direction. In order to describe a general vector, we introduce a vector basis, with as many linearly independent basis vectors as the dimension of the vector space we are describing. In this example, we are drawing in 2 dimensions and introduce the basis vectors e1 and e2, in this case taken to be orthogonal. The vector can then be written as a linear combination v1 e1 plus v2 e2. Using the Einstein summation convention, where repeated indices are summed over, this may be rewritten as v mu e mu. The choice of basis is not unique. Instead of e1 and e2, we could have chosen a different set of basis vectors e1 prime and e2 prime, and v could just as well have been written in terms of this other basis. In particular, since any vector may be expressed using any basis, the prime basis vectors may be expressed in the unprimed basis using the transformation coefficients a mu prime mu. Remember here that the repeated indices mu is a summation index. Writing out the relations explicitly in 2 dimensions, the prime basis vectors can be written in the following form. Here a, b, c and d are just numbers. Our vector space may be equipped with an inner product. If the space is Euclidean and we have chosen an orthonormal basis, the basis vectors satisfy the following relation. Here, delta is the Kronecker delta, which is 1 if the indices are the same and 0 otherwise. If the prime basis is also orthonormal, it is related to the unprimed by a rotation. In 2 dimensions, this can be explicitly written out as follows. Note that mu prime is equal to 2 and mu prime is equal to 1 is equivalent to the last of these relations, as the inner product is symmetric. The first of these relations is the equation for a circle of radius 1 and may be parameterized using an angle theta. This is also true for the second relation, but with a different angle. Using trigonometry, the third relation will simply state that the angles are the same, but with opposite sign. All in all, we find that the prime basis can be expressed in the unprimed using sines and cosines of a rotation angle. Geometrically, this is the angle between the basis vectors. In relativity, we will not be dealing with the usual inner product between vectors. Instead, we will look at the Minkowski inner product. For notational purposes, we will rename e2 to e0, as a 0 is usually used in relativity to denote a time direction. The Minkowski inner product differs from the Euclidean inner product in that the basis vectors do not satisfy the relation with the delta. Instead, the inner product of the basis vectors is given by the Minkowski metric tensor, eta. Like the Kronecker delta, eta is equal to 0 if the indices are different, and 1 if mu is equals to nu is equal to 0. However, for all other mu is equal to nu, it is equal to minus 1 rather than 1. This in a 4-dimensional spacetime means that mu and nu are equal to 1, 2 or 3. Coming back to changes of basis, the Lorentz transformations are transformations between vector bases which fulfill the Minkowski inner product relation with the metric tensor eta, just as rotations preserve the inner product being a Kronecker delta in the Euclidean case. Writing out the linear relation between the bases, again renaming e2 to e0, we have similar relations to those found in the Euclidean case. Instead of being the equation for a circle, we now have an equation for a hyperbola, which may be parameterized using a hyperbolic angle theta, and this also goes for the second relation. The third relation now states that the hyperbolic angles are equal rather than opposite. If you are not familiar with hyperbolic functions, it is a good exercise to work out these relations yourself. The final relation between the primed and unprimed bases are now a hyperbolic rotation rather than the rotation we found in the Euclidean case. A hyperbolic rotation does not rotate the basis along a circle. Instead, the new basis vectors will be ending on the hyperbolae. D squared minus c squared is equal to 1 and b squared minus a squared is equal to minus 1. The hyperbolic angle theta may be interpreted as the hyperbolic distance along the hyperbola, but we will talk more about this in a later lecture.